Picture this. You're at a truck pull competition in 1985, and there's this deafening roar that doesn't sound like any V8 you've ever heard. It's deeper, angrier, almost industrial. The crowd goes silent as a modified pulling truck launches forward with a violence that shouldn't be possible. Under its hood isn't some exotic racing V8. It's a diesel engine originally designed to move mountains, literally. And what you're witnessing is a Caterpillar 3208 industrial diesel doing something that would destroy any gasoline V8 in seconds, running boost pressures that would turn aluminum pistons into metallic confetti. We're talking 60, 70, sometimes over 100 psi of boost pressure. To put that in perspective, most turbocharged streetcars run 6 to 15 psi. High-performance builds might push 25 to 30 psi with extensive modifications. Racing engines might briefly survive 40 psi with exotic fuels and constant rebuilds. But these Caterpillar engines, they'd run triple those numbers all day long, pull after pull, season after season, without breaking a sweat. This is the story of how diesel engines designed for bulldozers, excavators, and industrial generators became the most dominant force in competitive truck pulling, and why no gasoline V8, no matter how built, could match their seemingly impossible boost tolerance. It's a tale of metallurgy, thermodynamics, and engineering philosophy that turned earth-moving equipment into competition-crushing monsters. To understand why Caterpillar engines could handle boost levels that would instantly grenade a V8, we need to go back to their birthplace, not a racing shop or performance division, but the hostile environment of industrial equipment. In 1964, Caterpillar's engineers in Peoria, Illinois, faced a challenge. They needed engines that could operate at full power for thousands of hours in the worst conditions imaginable. Desert heat, Arctic cold, altitude, dust storms, 24 hours a day, 7 days a week, for years on end. The resulting engine family, particularly the 3208 and later the 3406, weren't designed to be fast. They were designed to be indestructible. And that design philosophy would accidentally create the perfect platform for extreme boost applications that the racing world had never seen. Let's start with the fundamental difference in construction. A typical performance V8 of the era, say a Chevrolet 454 big block, used a cast iron block with cast iron heads. The pistons were aluminum alloy, the connecting rods were forged steel, and the crankshaft was either cast or forged steel depending on the application. These were good, strong components for their intended purpose. But the Caterpillar engines? They were built to an entirely different standard. And then the Cat 3208 featured a deep skirt block design where the block extended well below the crankshaft centerline. This wasn't for looks. It created an incredibly rigid structure that resisted flex under extreme cylinder pressures. The main bearing caps weren't just caps, they were massive girdles that tied into the block structure. Where a performance V8 might have 2 bolt main caps or 4 bolt mains in racing applications, the Caterpillar used a cross-bolted design with additional side bolts that created a virtually unbreakable bottom end. But here's where it gets really interesting. The pistons in these engines weren't aluminum, they were steel. Now, steel pistons are heavier than aluminum, which is why racing engines avoid them. The extra reciprocating mass limits RPM potential. But Caterpillar didn't care about high RPM. The 3208 was governed at 2800 RPM maximum. What steel pistons offered was incredible strength and heat resistance. An aluminum piston starts to lose strength dramatically above 400 degrees Fahrenheit. By 600 degrees, it's basically butter. Steel pistons maintain their strength well past 1000 degrees. The connecting rods were equally overbuilt. Where a performance V8 might use I-beam rods to reduce weight, Caterpillar used massive H-beam designs that were practically indestructible. The rod bolts were sized for continuous operation at maximum power, not occasional pulls down the drag strip. These rods could handle compression loads that would buckle typical automotive connecting rods, like soda straws. On the crankshaft was a forged steel piece that weighed nearly 140 pounds in the 3208. For comparison, a typical V8 performance crankshaft weighs 50 to 70 pounds. This massive rotating assembly wasn't just strong, it acted as a giant flywheel, storing rotational energy that helped maintain momentum under extreme loads. The journal sizes were enormous, spreading the load over a larger surface area and reducing bearing stress. Now, let's talk about the heads and valve train, because this is where things get really clever. The cylinder heads on these Caterpillar engines were designed for absolute reliability under continuous high boost. The head gasket wasn't just a gasket, it was a sophisticated multi-layer steel design with integral fire rings around each cylinder. The head bolts, or more accurately head studs in many applications, went deep into the block structure. Where a typical V8 might have 4 head bolts per cylinder, these engines used 6 or more, creating clamping forces that could resist enormous combustion pressures. The valves themselves were a work of art. The exhaust valves were made from Inconel, a nickel-chromium superalloy that maintains its strength at temperatures that would melt standard valve materials. These valves were sodium-filled in many applications. Inside the valve stem was metallic sodium that would melt at operating temperature and slosh around, transferring heat from the valve head to the stem where it could be dissipated through the valve guide. This technology, borrowed from aircraft engines, allowed these valves to survive exhaust gas temperatures exceeding 1400 degrees Fahrenheit continuously. But here's the kicker. The real secret weapon. These engines were designed from the ground up to be turbocharged. Not turbocharged as an afterthought like many automotive applications of the era, but fundamentally engineered around forced induction. The compression ratio was kept intentionally low, around 16:1 or 17:1, for diesel operation, compared to the 22.1 or higher that naturally aspirated diesels might run. This lower compression ratio left room for massive amounts of boost without creating cylinder pressures that would exceed the structural limits. And the turbochargers themselves were industrial units designed for continuous duty. We're not talking about small responsive units designed for good throttle response. These were massive turbos originally designed for stationary power generation or marine applications. The Schwitzer 4LHR was a popular choice, with a compressor wheel larger than a dinner plate. These turbos were so large they had their own oil circulation systems separate from the engine. They were designed to run at maximum boost continuously, not just in short bursts. And this is where the pulling competitors discovered something amazing. These industrial turbos could be modified to produce boost levels that seemed impossible. The wastegate would be welded shut. The compressor housing would be modified to increase flow. Multiple turbos would be compounded, with one turbo feeding another, creating boost multiplication that could exceed 100 psi and at 100 psi of boost, the intake air temperature, even with intercooling, could exceed 300 degrees Fahrenheit. The air was so compressed it barely resembled normal atmosphere. It was dense, hot, and violent. Any gasoline engine trying to run this kind of boost would detonate instantly, destroying pistons in milliseconds. But diesel engines don't have spark plugs. They rely on compression ignition, and the fuel isn't mixed with the air until the moment of injection. This meant detonation in the traditional sense was impossible. The engine could handle any amount of boost the turbo system could produce, limited only by the structural integrity of the components. Let me paint you a picture of what happened when pulling teams first discovered this capability. It was 1983 at the National Tractor Pulling Championships in Bowling Green, Ohio. A pulling truck showed up with what everyone thought was a joke, a Caterpillar 3208 diesel, where everyone else was running blown alcohol V8s. The alcohol guys were making 2,000, maybe 2,500 horsepower on a good day. They laughed at the diesel. Then the green flag dropped. The diesel truck hooked to the sled, and something unprecedented happened. Instead of the usual wheel-spinning, tire-smoking spectacle, the truck just dug in and pulled. The turbo whistled like a jet engine, the exhaust temperature gauge showed 1,400 degrees, and the boost gauge was pegged past 60 psi. The truck pulled the sled the full distance. Then it did it again and again. By the end of the weekend, the diesel had won its class, and everyone wanted to know how. The answer was in the fuel system modifications. These Caterpillar engines used inline injection pumps, essentially mechanical computers that precisely metered fuel to each cylinder. In stock form, they were limited to safe fuel delivery rates. But the pulling teams discovered these pumps could be modified far beyond factory specifications. The plungers and barrels could be enlarged, the governor could be removed, the delivery valves could be modified for increased flow. Fuel pressure could be raised from the stock 15,000 psi to over 30,000 psi. With these modifications, a 636 cubic inch 3208 that made 210 horsepower from the factory could produce over 3,000 horsepower. The larger 3406, at 893 cubic inches, could exceed 4,000 horsepower with extreme boost and fuel modifications. These weren't sprint numbers either. These engines could maintain these power levels for the duration of a pull, about 300 feet, or roughly 10 to 15 seconds of full power operation. But wait, there's more. The cooling system on these engines was another masterpiece of over-engineering. The water jackets were designed for maximum flow around the critical upper cylinder area. The coolant passages were enormous compared to automotive engines. The water pump was gear-driven and moved tremendous volumes of coolant. In pulling applications, teams would run multiple electric water pumps, oversized radiators, and sometimes even ice water injection systems. The engines could dissipate heat at rates that would overwhelm conventional cooling systems. The oiling system was equally robust. The oil pump was a gear-type pump that could maintain pressure even with hot, thin oil. The oil galleries were oversized to ensure flow to all bearings, even under extreme loads. The oil capacity was huge. The 3208 held 7 gallons of oil, compared to 5 quarts in a typical V8. This large oil volume helped absorb and dissipate heat while maintaining lubrication under extreme conditions. Now you might be wondering, if these engines were so superior, why didn't everyone immediately switch to diesel? The answer reveals another fascinating aspect of this story: pride, tradition, and the sound of screaming V8s die hard in the pulling world. Many sanctioning bodies initially banned diesels or put them in separate classes. They were considered an unfair advantage, too different from the traditional pulling engines to compete directly. But the diesel pullers kept showing up, kept winning when allowed to compete, and kept pushing the boundaries of what was possible. They formed their own associations, their own classes, and gradually the establishment had to acknowledge what was happening. Diesels weren't just competitive, they were dominant. The technical advantage went beyond just boost tolerance. These engines produced massive torque at low RPM, exactly where it was needed for pulling. A modified 3406 could produce over 3,000 lb-ft of torque at just 1,800 RPM. The torque curve was essentially flat from 1,400 RPM to the 2,800 RPM governor limit. This meant the engine could lug down under extreme load without losing power, where a high-revving V8 would fall off its power band and struggle. The durability factor was equally impressive. Teams running alcohol V8s were rebuilding engines after every event, sometimes after every pull. Pistons would be replaced, bearings checked, heads pulled for valve work. It was constant maintenance just to survive. The Caterpillar engines, they'd run an entire season without being opened up, change the oil, adjust the valves, Maybe replace a head gasket if things got really extreme. The steel pistons showed barely any wear. The bottom ends remained tight. These engines treated 3,000 horsepower like a lazy Sunday drive. Let me give you specific numbers that illustrate just how extreme these builds became. By 1987, a top superstock pulling tractor running a modified 3406 Caterpillar was producing approximately 3,500 horsepower at 85 psi of boost. The intake manifold temperature after the intercooler was 280 degrees Fahrenheit. The exhaust gas temperature was 14 to 50 degrees. The fuel system was delivering 850 cc of diesel fuel per injection event, compared to about 150 cc stock. The injection pressure exceeded 28,000 psi. The cylinder pressure at peak combustion was estimated at over 3,000 psi. And for comparison, a contemporary top fuel drag racing engine might see cylinder pressures of 1,500 psi for a few seconds. These pulling engines sustained twice that pressure for the entire duration of the pull. The connecting rod was experiencing compression loads exceeding 30 tons at peak pressure. That's the weight of about 20 cars pressing down on each rod 8 times per second, continuously. The metallurgical advantage of the diesel design became even more apparent under these extreme conditions. The steel pistons could handle the pressure and temperature without distortion. The cast iron construction of the block and heads actually worked as an advantage here. Cast iron has excellent thermal stability and resistance to pressure-induced distortion. While aluminum cylinder heads might lift or warp under these conditions, the iron heads remained stable. Then, the fuel itself provided another advantage. Diesel fuel has lubricating properties that gasoline lacks. As the fuel passed through the injection system at extreme pressures, it lubricated the pump, injectors, and delivery valves. Gasoline and alcohol fuels are solvents that wash away lubrication, causing rapid wear in fuel system components. The diesel fuel also has a higher energy density than gasoline or alcohol, meaning more potential power per pound of fuel consumed. But perhaps the most significant advantage was the combustion characteristic itself. In a diesel engine, the fuel is injected directly into compressed, superheated air. The combustion event is progressive, starting at the first droplets of fuel and continuing as more fuel is injected. This creates a relatively smooth pressure rise compared to the violent detonation that would occur in a gasoline engine at these boost levels. The diesel combustion event, while powerful, was actually gentler on the engine components than the sharp pressure spike of gasoline detonation. Untertechnisch end teams began pushing even further. Compound turbocharging became the next frontier. Instead of a single large turbo, they would use 2 or 3 turbos in series. A small high-pressure turbo would feed a larger low-pressure turbo, which would feed an even larger atmospheric turbo. Each stage would multiply the pressure ratio, creating boost levels that seemed physically impossible. 120 psi became achievable. Some claim to exceed 150 psi, though at these levels, even the instrumentation became questionable. Then, the limiting factor became not the engine's ability to handle boost, but the ability to get enough fuel into the cylinder. The injection pumps were being pushed to their absolute limits. Custom billet pumps were developed with larger plungers, stronger housings, and exotic materials. Electronic injection was still in its infancy, but when it arrived, it opened new possibilities for precise fuel control at extreme flow rates. The evolution of these engines in pulling competition drove innovation that would eventually filter down to commercial applications. Caterpillar's engineers watched with interest as pullers discovered the true limits of their designs. Some of the modifications developed in pulling competition, particularly in turbocharging and fuel injection, influenced future industrial engine development. The ceramic coatings used on piston crowns in pulling engines became standard in later high-output industrial engines. The intercooling strategies developed for pulling found their way into over-the-road truck engines. By the early 1990s, the diesel dominance in pulling was complete in unlimited classes. The sound of competition had changed from the scream of blown alcohol V8s to the whistle and roar of compound turbo diesels. The performance numbers had become almost absurd. A top unlimited modified pulling tractor could generate over 5,000 horsepower from multiple turbocharged diesel engines. The boost gauges now needed to read to 200 psi. The exhaust gas temperatures exceeded 1,600 degrees. The fuel consumption during a pull could exceed 10 gallons in 10 seconds. But here's the thing about this whole story that really matters. This wasn't supposed to happen. These engines weren't designed for competition. They were designed to dig foundations, generate electricity, and pump water. The fact that they became dominant in one of the most extreme forms of motorsport was entirely accidental. It happened because their fundamental engineering was so robust, so overbuilt, that they had capabilities even their designers didn't fully appreciate. Yetitas and the Caterpillar engineers built these engines to survive worst-case scenarios in industrial applications. They designed them to handle maximum continuous load in 120-degree heat or minus 40-degree cold. They built them to survive bad fuel, poor maintenance, and operators who might not care about mechanical sympathy. Every component was sized for durability first, performance second. Weight wasn't a concern. Complexity wasn't avoided if it meant better reliability. Cost was secondary to longevity. And in this design philosophy, created engines that could handle stresses that would destroy purpose-built racing engines. The pulling competitors didn't make these engines strong. They discovered how strong they already were. They just removed the artificial limitations, the safety factors, the conservative fuel settings, and let the engines show what they could really do. The legacy of this discovery extends far beyond pulling competitions. It demonstrated that diesel engines weren't just for economy and longevity. They could be absolute performance monsters when unleashed. It paved the way for the modern diesel performance movement, where modified pickup trucks make 4-digit horsepower numbers that would have seemed like fantasy in the 1980s. Every compound turbo diesel drag truck, every 1,000 horsepower daily driven Cummins or Power Stroke owes something to those early pulling pioneers who proved what diesels could do. The technical lessons learned from pushing these engines to their limits advanced diesel technology significantly. The understanding of boost pressure limits, fuel injection requirements, and thermal management at extreme power levels informed the development of modern high-output diesel engines. Today's commercial engines making 600 horsepower reliably in over-the-road applications benefit from knowledge gained in pulling competition. The story also illustrates a fundamental truth about engineering. Sometimes the best performance platform isn't the one designed for performance, but the one designed for survival. The Caterpillar engines dominated not because they were sophisticated or advanced, but because they were simple, brutal, and overbuilt. They won through sheer mechanical superiority, through metal thickness and bearing surface area and thermal mass. They proved that in extreme applications, durability and performance can be the same thing. And modern pulling has evolved even further, with purpose-built billet engines designed specifically for competition. But even these modern monsters follow design principles established by those industrial Caterpillar engines: steel pistons, massive bottom ends, extreme boost capability, and the fundamental understanding that in diesel competition, there's no such thing as too strong. Hence, the transformation of earth-moving engines into competition dominators remains one of the most unlikely success stories in motorsport. It showed that innovation doesn't always come from racing departments or performance divisions. Sometimes it comes from farmers and truckers and industrial mechanics who see potential where others see just another work engine. They took engines designed to build civilization and used them to redefine what was possible in motorsport. And today, When you see a modern pulling tractor with multiple turbos glowing red hot, producing enough power to pull a locomotive, remember that it all started with someone looking at a bulldozer engine and thinking, "Hurry, I wonder how much boost this thing can really take." The answer, it turned out, was all of it. Every pound of boost the turbo could make, these engines could take. They didn't just tolerate extreme boost, they thrived on it, demanded it, and rewrote the rules of what an engine could survive. That Caterpillar 3208 or 3406 under the hood wasn't just an engine. It was proof that sometimes the most unlikely candidate becomes the champion. It was evidence that over-engineering for one purpose can accidentally create superiority in another. It was a testament to the idea that in engineering, as in life, the strongest foundation often leads to the highest achievement. The Earthmover engines didn't just outsmart every V8. They outlasted them, outpulled them, and ultimately outlived them in competition. They proved that in the brutal world of truck and tractor pulling, the engine built to move mountains could indeed move anything, including the entire sport, into a new era. The boost levels that would have been called impossible became routine. The power numbers that would have been called fantasy became reality. And it all happened because someone figured out that the strongest engines in motorsport weren't built for racing, they were built for work. What's the most unexpected mechanical success story you've ever witnessed? Drop a comment below and share your thoughts on these industrial monsters turned competition legends. And if you want more stories about engines that redefined what's possible, make sure to subscribe. Until next time, keep those turbos spooled and those boost gauges pegged.